Okay, I should be live now. Google Chrome's crashed like 3 times trying to get this running. So please let me know if you can hear me. Yeah, hopefully that's working. It's going a bit weird, but that should be fine, I think. So can you all hear me? I can still see the chat. Close that. Cool, cool, cool. All right. So, let's see. All right. So, what I think we might start with, and probably the most applicable to the assignment, is two-dimensional dynamically allocated arrays. Okay, so in the last assignment we went about this and we had two-dimensional dynamically allocated, but only one dimension was dynamically allocated. And now we want to look at 2 dimensions being dynamically allocated. I wonder if I can get it up there. Looks pretty good. All right. So there's a couple of ways we can go about this, and we can go for simplicity and potentially just, I want to step through, there's a lots of ways you can go about this, but I'm going to step through a couple of ways to go about this. And one of the ways is the ways that I suggested in the assignment, but let's have a look at this. So let's do the way we're doing in the assignment firstly. So let's say I've got int x, I've got int y, and I ask the user for printf, enter x, y, and then I scanf, no, losing my mind. Oh, that's not very good. So I scanf %d, comma, %d. So this expects there to be a comma there. And then I'll put this in the address of x, the address of y. Okay. So this is going to be the starting point for all of our dynamic arrays in this case. Okay. Now, what we want to do is pretty much what we did in the last assignment, but we want to dynamically allocate our rows this time. So in the last assignment, we had set amount of rows, but we had dynamically allocated columns. So we can go about this very similarly. Now, when we did this last time, we created. So let's just have a look at last assignment's example. So in the last assignment's example, we had something like int star w6. Okay, and this was an array of 6 pointers. Okay. Now, something to note is that we also have some pointer pointing to the start, and it has type 6. But if we wanted this dynamically allocated, we can see that this here is of type int star. And so we could potentially point to the start, not with W, but with a int star star. Okay, because the address of this has to be held by an int star star, because if this variable here is an int star, then to hold the address, we need an int star star. So we're going to get rid of this 6, and I'm going to put int star star here. Now, one thing you need to be aware of, and it won't really affect how you do this, but this and this are not the same, okay? And they're not actually the same type. You can kind of, for now, just think of them as the same type. This gets kind of complex, the difference between these two. But when we have pointers and arrays, things start to get a little bit more difficult. So don't worry too much about the type here, but you have got a pointer to this. So it is of type int star star in some regards. But it also knows the size, which is an interesting addition to that, just because you have given it a constant value, where here you haven't. Okay, so we basically want the same thing. So we can have int star, oops, star star w, and now what I want. So I've got my pointer, which is w. Okay, it's a single pointer. So it's type int star star. So this is allowed to point at basically any int star. Okay? So we can use malloc here. Okay? And we can say size of int star times, let's say x. Now, if the user enters x as 3, and we're using a 32-bit system, then size of int star is going to be 4, and x is going to be 3. So 3 times 4 is 12, and we get 12 bytes. So we end up with an array of 12 bytes. Now, because this int star is pointing, int star star is pointing into it, it is treated as int stars. And you'll see why I say this a little later, because our box and pointer diagrams are kind of misleading in some regards. And I'll show you why a little later for the third example. All right, so here I'm just going to have int star, and these are my 3 pointers. Okay. Now, because this is an array, if I want this pointer, I can say w0. If I want this pointer, I can say w1. If I want this pointer, I can say w2, just like before. So now, I can quite easily do what I did in the first assignment and just go for, let's introduce an I variable. For I equals 0, I less than x, I plus plus, and we can go from here, we can just go w, I becomes malloc size of, and because these are int pointers, we want to be pointing at ints, and times that by y. Okay, so if the user enters y, let's say 4. Then each one of these will have 4. Okay, and we end up with a 2-dimensional array again. Now, one thing, I'm not sure if I mentioned it last time, but I will mention it now. So now I can do things, so I'll mention something soon. Now I can do things like W, 0, 1. Okay, becomes 4. And this first one is looking at this, and we go 0, which is this one, and then we go here, and then we've got 1. Okay, so this still works. Okay, so with these brackets, and I'll show you how this works. I made a video earlier, but I just wanted to re-clarify some stuff because I kind of made a little mistake in it. But this first 0 is talking about this array, the second one is this array. And so this now has a 4 in it. Now, this is well and good. So we end up with a matrix like this. Okay? But doing it this way actually allows us to do something a little tricky. It's not bad, but I need some more room to do it. So I'm just going to move some of this stuff over. Precision there. So I'm just going to move that over. What I'm going to do is change this. So using this method, and you won't need this in the assignment at all, but it's quite handy because you may have lists that look like this. So I'm going to put y plus I here. So in this case, on the first iteration, we have y plus 0. So we have 4 plus 0. So we end up with an array of 4. But on the second iteration, we end up with 4 plus 1. So we end up with 5. On the third iteration, we end up with 4 plus 2, and we end up with 2 more. So we can have something that looks like this. So you can see using this method, we can have variable sized columns. Okay, so the columns, the number of columns is not a fixed number for this. Now this can be dangerous and worrisome. However, if done right, this can actually be used for lists. So if you have a bunch of pointers to a bunch of lists, so this first pointer may be pointing to a list of dogs, and this one's a list of cats. Obviously, they're going to be different sizes, and you just need to keep track of where the end is. And you can use realloc to make it bigger and smaller as these lists change. Okay, so this can actually be quite handy. It's just because it's a two-dimensional array doesn't mean that they have to have equal rows and columns. Okay, but you have to be careful because obviously trying to write in any of these can cause a segfault. Okay, does that make sense so far? So it's just a little bit of an extension on what we've done already. But you'll notice that this is a double pointer because we need to point to our array. And then we have our ints there. Good point. So someone mentioned that lucky we can still use our array subscripting. So this is where it gets interesting. So let's do a set of two-dimensional array where we don't use subscripting. And personally, subscripting isn't the best thing for speed, but it is for understanding. However, we can do a two-dimensional array where we can't use subscripting after we've created it, but it will create pretty much the smallest array. So you'll notice here that for every row, I have to introduce a pointer. So we have, let's just do the standard example for now. So here we have, we have y times size of int plus x times size of int star plus 1. 1 being this one. And that's the total, oh sorry, I shouldn't have said 1 times size of int star star. Okay. So this is the total size of our array in this case, if we had this code. But what if we wanted to just get rid of all that memory? We can actually do that. Okay? So if this is significant, we can do this. However, we lose our ability to use subscripting. So I'm going to steal my x and y again. So this method's the method that you'll use in your assignment, but let's look at some other methods for fun. Well, not for fun, but understanding. A bit of fun, maybe. I might actually create another layer. All right, so another method that we could use, which reduces memory, is we will not have a double pointer. And I'm just going to create a huge block of memory. And I'm going to use just an int star and treat everything as its regular type. So let's say int star w becomes malloc x times y times size of int. And the reason I'm doing this is, remember, if I want a, let's say a, I might make it even. So if I have a 4 times 3 matrix, all I really want is 12 ints. Okay? So let's have a look at this. With this, we create our move over a bit. So using this method, we end up with our pointer called w again, but it's of type int star. And it points, let's say x is 3, y is 4. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't know why that one's so big. Do that again. Just so put a bit more room. Four, so we're 12 now. Beautiful. Okay, so we end up with something that looks like this, and these are all ints. Okay, but we've lost our rows and columns. However, do we really need to know where the rows and columns are, given that we can do some quick math? Okay, so X is the number of rows, Y is the number of columns. So let's say, so I'll just indicate where the rows end. Let's say I wanted to enter something in row 1. Okay, this is row 1 because this would be row 0. Column 2. So what I could do, given that, I can dereference W. I can add what am I doing? Where am I? No, we're not doing that. We'll get to that. That's the next part. So I can add, sorry, where's my columns? R times R. Yeah, R, sorry. R times X plus C. So we start here. We go 1 times 4, so we add 4, so meaning we're here, and then we add 2 columns, so we are here. And now we can put stuff in there. Okay. Sorry. Now, doing this, we can go either way. We could use this as being rows first and columns first. It doesn't matter. Oh, shit. I made a mistake. It's 3 here. So I'll just change that to a Y. Okay. And yeah, that's fine. Okay, that should be Y. That was my fault. You just flip these if you want it the other way around, because it doesn't know which is a row and a column. Okay? C's this, R's this. So I'm just talking about this one. Row 1, column 2. Column 2, column 1, column 0. Okay? So with this, we can do basically everything that we did before, except for we just change these two, depending on the row and column we want. Okay? But this is nice in some regards, especially if you're iterating, because you can just keep iterating over and come back and do a bunch of stuff here. But it does mean that you can't use array notation. You can somewhat use it, but you have a problem. So I can go W, let's say 8, okay, and set that to 4, meaning it will go here and set that to 4, but I can't put the double brackets, okay, because first pointer, second thing in the array, but we don't have that here. All right. However, we can do this. W r times y. Can we? Yeah, we can. Plus c, because that should come out as 4 plus 2, which gives 6, and that is 6. Okay? Which equals 4, let's say. And that will change it to 4. So we could go either way, but you can see that the subscripting with 2 brackets doesn't work anymore. Right? Does that make sense? It's highly unlikely that you'll use this method right now, but it can be quite helpful. Sorry if I wasn't very clear. I'm a bit tired. All right, so what I want to do now is, this is up to you. So we can talk about another way to create a 2D array, which is kind of nice. It allows all the same things, but it's also a bit faster. But I have to show you something that's not very examinable in this subject. Like, creating it this way is not very examinable either. But it depends if you want to learn that, or do you want to learn something about this week's content. So we can learn something interesting, or we can, but it's not examinable, or we can go on to stuff for this week. You decide. Do that. Just want to. So there's something interesting is about 2D arrays, but you don't need it for the assignment, and you don't need it for the exam. It's just interesting. Is anyone else here? Please use the chat. Okay, please use the chat. It's really hard to talk for hours without some interaction. All right, where the hell did YouTube go? Okay, well, I might just go through this quickly and then I'll wrap up. Not as many people as I could would be. Sorry, I'm just trying to put something. Cool. Okay, so basically what we want to look at is files. Okay, so files are basically somewhere we can store stuff. Okay, we can also have streams which act like files. So some examples of some streams, let's say, so you've been using two already, standard in and standard out. Okay. Standard in is generally associated with your keyboard. Doesn't have to be, but, and standard out is usually a screen. Okay. So this here, these act like files, these streams. Okay. The only special thing is that we can use standardized functions to use these rather than file functions. However, all your file functions will work perfectly fine on these because they act like files. Okay. So with files, in the lab this week we'll look at a audio file, but most of the files you'll see are going to be text files. And basically, it's the same as your screen in most cases. And you can treat it that way. So, what do I want to start with? Yes. So the first thing I want to mention is storing in binary or storing it as text. So you're already aware that 62, if you store that as text, it's going to be the ASCII character 6 and the ASCII character 2, or we could store it in binary. Okay. And so binary files will actually save you space in most cases than writing text for everything. Okay, so let's look at the most important things. So if I want to play with files, I first need a file pointer. Okay, so this is capital FLIE star. Okay. And we can call this, let's just call it file pointer. Okay. Now, this points at the file. Okay. So it can change. You can point it to multiple files. It's not always going to point at the same file. So we also need to open a file. So to do that, we use the function fopen. Okay. So we can go file, we can go file, ptr is assigned, fopen, and then we have two arguments. The first is the file name, so I'm just going to write happy.bin. Okay. The second is the mode. And this is actually a car star that it's expecting. And we have a bunch of different modes. So we have R. So you can see it's a car star because it's a string. And this means reading. So you want to open it just for reading. W means writing. A means appending. So if you've already got a file, then it'll append to it. Now, two things that are important here. If the file doesn't exist with these two, it will create them for you. Okay? However, this reading one, obviously, because it's just reading, it needs something to read, so it's not going to create the file for you. We also then have R+, which is reading and writing. We have Write+, which is also reading and writing. But this will actually, if the file exists, basically delete what's there. Okay. And we have A+ as well, which is reading and writing and appending. Okay. So I might put this list up on LMS somewhere. But let's open a file for appending. Let's say. Let's just open for writing, right? Let's go. Just remember if R+. Just one second. I can't remember. Yeah, but that was right. Okay. So let's go W+. Okay, so if it exists, it'll open it, but it'll delete what's there, and we can read or write to it. Okay. So we now have a file somewhere, and this file is going to be in our local directory. We can use .. / and things like that in here if we want to go back and open something. Now, with our files, you have to do something quite important. And this is where a lot of people get into trouble with files. So with malloc, what do we have to do before we finish the program? Free. So with files, we don't actually have to free, but we actually have to close our file. And we use fclose and then the file pointer. Okay? And the reason we have to close it is so that the data is written to disk. So with the file pointers, it may not write. So let's say your file's here, and this is your file pointer. It may not write directly in there. It may actually buffer it just to save speed and time. And so it might put a bunch of data, and there is other commands so you can dump it in there. But we won't go into that. We'll just do fclose for now. When you close it, it'll actually finish off and write it all and then close it. Okay? Just to be careful. Okay? So you do need to close it, or else most of the time your data won't actually be written to the file. Okay. But you can flush that buffer if you need. Now, what was I going to say? One other thing that you should do is something I suggested with the malloc, is you can check if this returns null. So if you're opening for reading, sorry, and it returns null, then you can just say printf file does not exist. Okay. So you can check if the file exists or doesn't exist. However, remember some of these, like WP+, will actually create the file if it doesn't exist. All right. So what we're going to look at is, let's start with text files. The text files are quite easy because you've done them all already. So you've seen printf and you've seen scanf. So let's just do a quick example. Let's say I've got int main fprintf standard. God, that's annoying. Standard out, and then we'll go hello %d line. We'll just put an 8 there. So cool. So what happens here? So as we said before, standard out is our screen. We've seen printf before, but not this fprintf. So fprintf expects a file pointer here. Okay, and we created one before. But as we said before, a string also acts like a file. So this fprintf prints hello 8 to the screen. Just like it would do exactly the same thing as printf hello %d/n 8. Okay. Now, this can be quite helpful, and actually changing where standard out is can also be quite helpful, because it doesn't always have to come to the screen. Your standard out could be something else. But we can see here that standard out is a file pointer. Now, same thing, if we want to scan from the screen, well, not from the screen, from the keyboard, sorry, we can use something else. Oh, whoops. We can use fscanf. Let's make a variable called w. And now I can do standard in, and just go %d address of w. Okay, and this will act the same as scanf %d address of w. Okay, does that make sense so far? Yes, no, maybe, maybe not. Okay, so with our files, text files, and I might actually, so I'll change this from a binary file to a text file. However, it doesn't actually matter until we get to the next stage, but it actually really doesn't matter. There's a little bit of lying going on there, but that's always fun. Okay, so I can do something like this, f_f. I can go file pointer, and I can then go hello file /n, and then I can do, I don't need any other arguments for that. So this happy .text now has in it hello file. So if we open this up in a text editor or using Vim or something like that, we should see this text. Now what I'm going to do is create another file pointer, so I'll call this file pointer 2. And I'm going to fopen. We can read from this one, but let's just read. No, I want to do something different. Yeah, I'll do something different because and we'll call this sad.txt, and we'll open this up for reading. Now, one thing that so this is happy.txt, and this is sad.txt. So this has the characters 61 in them, and these are characters, okay, so they're text. However, scanf deals with that, because when you're entering on the keyboard, you're actually getting characters. So you're getting the character 6 and the character 1, but scanf is able to turn that into an int or whatever type it likes. So I'm going to go fscan, I need a variable to store the result. Let's go int w. So we'll go fscan f file pointer 2 percent. What are we doing? Int, sorry. So d address of w. And now in w, I should have the value 61. Okay. And then from there, I can go fprint f file pointer %d w. And so this should print into our other file. We had a new line, so that's okay. So we'll put 61 here. Okay. So that's all well and good. Now, one other thing that we should be aware of is EOF. So this is end of file. So the very last thing on the file is the end of file character. Okay, so wherever the file ends, there'll be an end of file. And we can actually check for this. So we can keep scanning until we get end of file or 0 things read. So a scanf, to check if there's nothing left in the file, we can just compare it and see if it returns one int. So we know that scanf and fscanf return the number of things read. Okay, so we can put that in an if statement if we want to check if there's something there. Okay, and that's basically the very basics of Text files. They pretty much act like the screen, but if you want to check for the end, just check how many things you've read from your fscanf. If it's not what's expected, then it means you've reached the end of the file, or some of your files corrupt, or it's in a different format than you expected. Right, and that's files for you. Does that make sense? So I'm going to have a quick little break, and then we'll cover binary files, and then we might just wrap it up there. Or we can go over something. So I'll be right back. Okay, so I am back. So the next thing I just want to quickly cover is we've talked about files. But I also mentioned binary files. Well. And so if we want to write and read binary files, it's slightly different. So let's say, what am I doing? Sorry. So I'll just grab. So let's say I want to store the number 6,253. Now, in a text file, this would be stored as 6253. But in a binary file, this would be stored as 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1. Now, this here is 2 bytes. So this could be a short. If I had an integer, then it would be a lot longer. Now, I might also mention something else, which is going to confuse you. So, I might actually talk about something else first, because this is kind of important for next week's content. And this is Indian and big and little Indian and the difference between them. So when you store memory on a computer, let's say I've got, actually an example before was kind of nice, so I might keep that there. So let's say I've got an int x and I store, what's the number? 6253. Okay. Now, let's say this, I might actually make it a little bigger. We saw our memory diagram in the past, and we know x needs, on a 32-bit system, so a 4-byte int, which is going to take 4 bytes. Each one of these has an address, so let's just call this address 0, 1, 2, 3. Okay. And even though we can't actually, I might actually change this to 8, 9, A, B. I don't like using 0 because you shouldn't really. All right. So the common thought would be that if I had to store this number, which is this number, in memory, it would look something like this. Okay, so this would be your common logic that if I convert this number to binary, it just goes into memory in the same order. However, I've lost my chat. However, this isn't always true. So this is called big Indian. And on a big Indian system, this is how the memory is stored. However, on a little Indian system, and you'll find out what type the Unix system is this week, it's actually going to store it like this. Zero, 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 and this is little Indian. So you can see with the little Indian that the bytes are in opposite order, but these bytes haven't changed. Okay, so it's still 0, 1, 1, 0, 1, 1, 0, 1. And so if we were to read this, we would read it this way. Sorry, wrong way. If we were to read this, we'd read it backwards. Okay, so it's 0, so that we end up with this again, where on a big Indian system, we'd read it forwards. Okay? Does that make sense? And when I say backwards, you're reading this whole thing first, then I'll show you exactly how you'd read it. Because so you'd read this whole thing, then you'd go all the way back over here, then you'd read this whole thing, then you go all the way back to here, then you'd read this whole thing, then you go all the way back here, then you'd read this whole thing. Okay? So in the byte itself, you still read from left to right, but outside the bytes, you're going backwards. Did I just confuse you, or did that make sense? So it just stores the bytes in the opposite order for a little Indian system. Make sense? Cool. All right. So now I want to read and write to a file. And depending on if it's little Indian or big Indian will make a difference. Okay? Because of how it's written to a file. Because if you're writing to a file and you're working with a little Indian system, and then you try and read it from a big Indian system, what's going to happen? It's going to think this is a completely different number. Okay? So let's just have a look at binary files to start with. So there's only a couple of differences. So we still have our file pointer. Let's call it FP. And we use fopen again. And we give it a file. Now this could be any file. It could be a text file. But if you want a purely binary file, then you just could call it a.bin. Our WAV files we're going to use as binary files. And then here, we can open and write, etc. like normal, but we usually add a B here to indicate that it's a binary file. However, it shouldn't really matter if you add that B or not. Now, with our reading and writing, if I use scanf with a binary file, let's say this binary file has this in it, it's not going to be able to understand this. Okay, because it's a fscanf and fprintf are expecting text. Okay, so they're expecting character pointers into them. So even if I enter this, it's still characters, even though we change it to an int. Where a binary file is just expecting the purely binary. So we can read from a file by going f_read. So I'm going to introduce an int w. Okay. And we're going to work with a big Indian system for now because that's how I've written it out there. And I'm going to give it my file pointer. Then I need to basically, oh no, that I want, that's not where the file pointer goes, so let me just think for a sec. So we want the address of W to start. And then we want the element size. So the element size here is 2 bytes. Okay. Then we want the count. So there's only one of these. Then we want the file pointer. Okay, so this is going to store the result in W. It's going to read 2 bytes, only one of them. So this is if you have an array, you can have a count of these. And then we have our file pointer. So this will read this and store it in our W. Okay. Now, the problem here is that it's going to read these 2 bytes and store them in W, but what part of the int is it going to write into? And so this is where we end up getting into trouble. So here, we really should be using a short, because if we use an int, then our 2 bytes that don't get written into have still not been initialized. And we actually end up with a different number because it's writing to these two, depending on the type of system. So it is important that when using f_read and write, that you are using the right types. And this should be write plus in this case. We can also do an f_write, and this will take the address of where to start from. 2 for 2 bytes want to be written, 1 because we only want to write 1, and then file pointer, which is our file pointer. So this address could be an array, and we could, so let's, for example, go short W2, and I can put a 2 here, and in W0, so I don't actually need the address anymore because it is a pointer. In W, we'll now basically, the first index will have one number and the second index will have another number. And in this example, we'll write the first number and then the second number. Does that make sense? This stuff would be good to have an example, which this lab this week will help you with. But this is a good little introduction to it. Okay. Because you really need a lot of text and stuff to play with to really get the file stuff. All right. But that's basically files. Okay. f_read and write do get difficult because you have to consider the size of your type and if you've got an array. But they can be quite powerful in storing stuff in a very small amount of space compared to text files. Text files use way too much space in a lot of cases. So if you're collecting a large amount of data, usually you want to use f_read and write because you'll cut down your file size massively. Okay. Now, I'll open up the lab shortly. I just got to make some changes to it from last year. But it is good to play around with. However, you need to use LabCS5 to make sure it works properly, okay? Because it won't work how you want it to otherwise. So I'm just giving you that warning. All right, that sound good? All right. Is there any questions? I'm pretty sure I give you all the very complex. Yeah, I give you the complex writes and reads anyway. But there's a very good example in the lab, so I might actually open up shortly. And I give you the code for it. And it'll show you how the arrays are written. Okay, and that's step 10 of the second one, if the numbers stay the same. It's a really good example of showing you this count, because all the ones you're doing, the counts are just going to be 1. Because with arrays, it starts getting a little bit confusing, but not overly confusing. Okay. I'm thinking we might finish off there. Because I've got a fair bit to do, and also got to mark your assignments. So this is just a quick heads up of files. Make sure you read the reading notes from this week. It also has very similar things. And yeah, sorry if it was a little bit slow. This one, I'm a bit tired, unfortunately. So enjoy the rest of your weekend, and hopefully we'll have everything marked by next week. And if not, it'll be Bo's fault. Other than that, all good. If you have any other questions, yeah, we can do more about the assignment. You have enough to do the first stage. So ideally, well, we can go over it quickly. I might do that because that's easy for me. Also, try and encourage people to come to the help sessions. I haven't at this stage got any funding to run them before the exams, and I would. So I just need people to show up to them so that I can encourage. The running of more of these before the exam. Because last year I think I did about 20 hours worth before the exam. People finally showed up to them when it comes to exams. Yeah, let me find the assignment. So we've done function prototypes. We've done structs in this week's lab. We've done global variables. We've done macros in the lectures. We've also done global variables in the lectures. We haven't really used global variables in the labs, but it is in the lectures. Step 8 and 9, well, that is using the functions that you create. So initialize the board using the appropriate function. So initializes the board using the appropriate function. So you've got initialize mine board or initialize mine values. And they're the two initializations. So I think you can work out, given the names, which one does the board. Obviously, because it's a function, we have to call it. Okay, so here, I think you can work out what happens. It's a function call. And then prints the board. I think you can work out which one that is. And it's just a function call for that. And that's step 8 and 9. Okay, they're just function calls to the appropriate functions. Okay. So you need to implement these. So create, let's look at the print one. Let's look at this one. Create iteration variable, I and j. So iterate, so you've got a for loop within a for loop or whatever loop you use. And then set a status byte for each location, so you know you've got in the structs somewhere. Where's those structs? There they are. You've got a status byte. Then create variables x and y, create a loop using rand. Now, one big thing, do not seed rand. If you don't know what that means, don't worry. Test the mine bit, and if it is that case, then do that. It's pretty self-explanatory for these because this is stage 1. You'll notice that there is a bit of bit manipulation, so go back to very early on in the subject. I think it was week 4, we did bitwise stuff. So in the initialized mine values, there will be some bitwise stuff. Now you'll notice we've got a function calling a function here, which is perfectly fine. We did that in the second assignment. And then the mine board one, there's not as much instructions, but you can see that you're using these macros, hence it's going to be bitwise stuff again. And make, move, and uncover zeros and get moved up part of stage 2. Okay. And if you get up to, if you finish stage 1, it should run and it should set up the board and print just an empty board to the screen. However, what you can do is basically manipulate the print mine boards function so that it prints the opposite. So don't print out the covered location, print out everything except for the covered, and you should see the game as if it was finished. And that may actually help you in debugging. Okay? Because obviously if you're covering everything, then you'll just see a big block of hashes. Okay, and you won't know if you set it up correctly. But if you print everything while you're just debugging, so this says print if revealed, but maybe you should print if not revealed for a debugging, and just print M or dash or the number, and you should see this instead, rather than all the hashes. Okay, so that's just a suggestion in helping you solve some of the problems. Does that make sense? Because at that stage, you'll just be printing hashes otherwise. All right, I might leave it there. If there's any other questions, just put them in the chat.